This research paper introduces a novel control scheme for robots utilizing cellular-like redundant binary actuators, such as air muscles, dielectric, piezoelectric, bioartificial muscles, and shape memory alloys. These soft robots have the potential to outperform traditional electric gear motor systems in terms of reliability, force-to-weight ratio, and cost. The proposed control method addresses the challenges of discrete actuator inputs, complex system modeling, and cross-coupling between actuators. Soft cellular robots offer several advantages, including reliability, fault tolerance, lightweight design, safety for human-machine interaction, and low production costs. An example of a soft exploration robot concept is presented, demonstrating the potential for these robots to withstand impacts and actuator failures, as well as their potential use in various environments. The control strategy employs influence vectors to determine the optimal combination of actuators needed to achieve a desired system output, such as position or force. For position-controlled tasks, a probabilistic approach and genetic algorithm are used to identify the best actuator combinations. For motion-controlled tasks, a sliding mode approach and independent recruiting decisions for each actuator are employed. Experimental results on a 4 degrees of freedom binary manipulator with 20 actuators demonstrate the effectiveness of the proposed method, including its ability to tolerate massive perturbations and numerous actuator failures. Additionally, the use of a monopropellant source to power air muscles and thrusters for hopping motions is discussed, which could be beneficial for exploration robots. The simplicity and miniaturization of binary control strategies are emphasized, eliminating the need for low-level control loops and simplifying control hardware. This approach enables the development of more efficient, reliable, and cost-effective robotic systems. This paper addresses the challenge of controlling soft, cellular-like robots with binary actuators, which cannot be modeled accurately using analytical models. Unlike traditional open-loop control strategies, a closed-loop approach is necessary to reject model uncertainties and external perturbations. Existing literature on binary systems control focuses on high repeatability open-loop robots with perfectly constrained systems, which is not applicable to soft robots. Some closed-loop techniques, such as broadcast feedback and force-based control, have been proposed, but they are limited to single-output systems or require a notice-elements mathematical description of the system, which is difficult to construct for soft robots. The proposed approach presents a closed-loop control scheme for multi-DOF binary systems based on the concept of influence vectors. Influence vectors are vectorial quantities resulting from the action of individual actuators, identified during an initial startup calibration. The set of influence vectors forms an experimental input-output model to predict the evolution of the system for given actuation commands. For the static scheme, influence vectors are the individual steady-state effects on the state vector x, describing the controlled DOFs of the system output. For the dynamic scheme, influence vectors consist of force quantities when all DOFs are constrained. The influence vectors can be related to their force vectors by a stiffness matrix, assuming a linear system. The proposed control scheme is experimentally verified on a soft polymer binary robot, demonstrating its effectiveness in tolerating massive perturbations and numerous actuator failures. The approach extends a previous preliminary demonstration, providing a formal presentation and exhaustive experimental results. In point-to-point control, the static control scheme focuses on achieving a desired final position, disregarding the path taken. This scheme involves finding an optimal combination of binary actuators to recruit, represented by a switch vector B, to correct the static state error Z, which is the difference between the desired state vector xd and the current state vector x. The system's evolution is described by a set of difference equations, where the state vector x and actuator input vector u are updated at each step. The influence vectors dk, accounting for the current actuator input state, are updated using the XOR operator. In fully linear systems, these influence vectors remain constant, while in nonlinear systems, they can be corrected using the state vector and actuation inputs vector, similar to feedback linearization. The updated influence vectors dk are used to compute a first-order linear approximation of the state changes increment x for a given switch vector b, using the superposition principle. This approximation is expressed as A equals jb, where J is the Jacobian matrix of the state vector x over the switch vector b. The controller must solve the inverse problem, finding a switch vector b that will create a state change increment x equal to the static error z. Since b is a binary vector, the solution set is discrete and finite, and a solution is computed by minimizing a cost function defined as the norm of the resolution error ER. This is achieved by exploring the forward solution space using a search algorithm, such as genetic algorithms or neural networks, under the binary constraint of b. The error correction process is performed iteratively, using local linear approximations, until the error becomes acceptable. This makes the controller robust to perturbations and actuator failures. However, the static scheme has a major drawback. It requires waiting for the stabilization of the states between each iterative correction. The convergence of the controller iterations depends on the linear approximation remaining a good approximation of the system. Optimizing the probabilistic cost function in robotic control algorithms is crucial for minimizing both resolution error and approximation error. To address this, a new probabilistic cost function is proposed, which considers the probability of arriving in a target zone, defined as the inverse of the probability of achieving the desired state within allowable errors. In corrections involving multiple actuators, error addition and higher-order coupling effects can significantly impact the system's behavior, making it essential to account for approximation error. To quantify this, a measure of approximation error dispersion is introduced as a function of the number of switching actuators. If individual error contributions are equal, the total dispersion can be calculated using the square root of the number of switching actuators multiplied by the individual dispersion contribution. The new probabilistic cost function is defined as the multiplication of individual probabilities for each degree of freedom, assuming independent error distributions on each DOF. The behavior of the probability density function for one DOF is illustrated, comparing solutions with different resolution errors and approximation errors. The optimal solution is identified as the one with the larger area under the probability density curve for the specified target zone, highlighting the importance of balancing both accuracy and precision in the control algorithm. By considering both resolution error and approximation error, this approach enables more accurate and precise control in robotic systems, particularly in scenarios involving multiple actuators and complex error interactions. A novel control strategy is proposed for a soft polymer robot actuated by 20 binary air muscles, designed for precise medical interventions within a magnetic resonance imaging system. This strategy consists of two components: a static controller that prioritizes solutions utilizing a minimal number of actuators, and a dynamic controller that employs a bang-bang sliding mode controller. The static controller minimizes actuator switching activity, reducing energy consumption and mechanical cycling. The dynamic controller computes a composite vector S as a weighted sum of the state error vector and its derivative. It then checks each actuator to determine if its updated force influence vector aligns with the direction of the composite error vector S, recruiting the actuator if so. The bang-bang controller's simplicity eliminates the need for computation-heavy search algorithms, making it suitable for real-time control. By considering only the directions of influence vectors, the control law can utilize updated displacement influence vectors directly, without requiring a stiffness matrix K. The proposed controllers are validated on a binary robot prototype with 4 actuated degrees of freedom. The experimental setup employs 2 lasers to project the axis of the needle guide on 2 planes, with 2 cameras capturing the positions of the laser dots. A Python script running on a laptop implements the control algorithm, with a LabJack U3 card handling I/O. State sensing involves processing camera images to find the centroid of the laser dots, then transforming camera coordinates to real-world coordinates using a perspective projection. The position vectors P1 and P2 are transformed into virtual end-effector states in a XY workplane, where the target is located. The rotation r of the laser line is defined as the unit rotation axis vector multiplied by the rotation angle. Experimental results demonstrate the effectiveness of the proposed control strategy for the soft polymer robot, showcasing its potential for accurate medical interventions within an MRI system. In the kinematics of the robot, the focus lies on the end effector position and its state vector in a 4 degree of freedom workplane. Experimentally, the approximation error distribution is evaluated for varying numbers of switching actuators, revealing an increase in error with the number of actuators. Notably, the error is found to be uncorrelated with factors such as distance to the base point, number of already on actuators, and motion directions. The standard deviation of the error on each degree of freedom is computed from the experimental sample, resulting in approximately 0.35 square root SN millimeters on Tx and Ti, and 0.025 square root SN degrees on Rx and Ry, where Sn is the number of switching actuators. Three cost functions are considered to define the value of a given switch vector B for a given situation. These include the norm of the resolution error, the inverse of the on-target probability, and the norm of the resolution error plus a penalty proportional to the number of switching actuators. Experimental evaluation on the prototype for 3 static translation-only targets reveals a significant performance improvement for the 2 cost functions penalizing the number of switching actuators. No difference is found between the probabilistic cost function and its simplified proportional version. Consequently, the simplified cost function is used in the remaining experiments due to its faster evaluation time. An optimization algorithm is presented, which finds a switch vector B minimizing the cost function during each iteration loop. This algorithm optimizes a solution in approximately 0.3 seconds, which is acceptable given the 3-second delay imposed between each iteration to allow the robot to reach a steady state. The optimization process employs a 2-stage genetic algorithm approach to determine the optimal solution. Initially, solutions with 3 or fewer switching actuators are evaluated, followed by a widespread genetic algorithm that optimizes the solution. The best solutions from both searches are then inserted into a more local genetic algorithm with fewer members but many generations to complete the optimization. The genetic algorithm utilizes random seeds generated as binary switch vectors with 4 switching actuators or more, and employs roulette wheel selection, segment-based crossover, and bitwise mutation. To evaluate the static controller's performance, 3 randomly selected targets are used, with a 3-second delay between each correction to allow the robot to stabilize. The results for translation-only, rotation-only, and simultaneous translation and rotation targets are presented in figures 13, 14, and 15, respectively. Notably, the static controller achieves sub-millimeter accuracy for translation-only targets, with an average of 4 iterations. However, its performance is limited for simultaneous control of 4 degrees of freedom due to the discrete workspace of the 20 actuators in the binary robots. The controller's ability to reject perturbations and operate in the event of actuator failures is demonstrated in figures 16, 17, and 18. The controller can correct perturbation-induced errors and adapt to actuator failures, although system resolution diminishes with each failed actuator. Table 2 presents the results of the controller's performance for up to 10 actuator failures out of 20, highlighting the non-deterministic nature of the controller due to random seeds. It is essential to interpret the results with care, considering the potential for approximation errors to cancel out resolution errors in rare situations. The static control experiments demonstrate the system's response to perturbations and undetected actuator failures, as shown in figures 16 and 17. Table 2 summarizes the performance of the static controller under various actuator failure scenarios, both detected and undetected. Notably, the results indicate that the controller can adapt to failures, albeit with some performance variations. For instance, Target 1 exhibits better performance with 10 actuator failures than with no failures. This anomaly warrants further investigation. Dynamic control experiments were conducted, despite limitations imposed by camera-induced delays, which restricted the control bandwidth to 5 Hz. Figures 18-21 present the results of dynamic control with static targets and trajectory-following tasks, showcasing the controller's potential despite inherent chattering, characterized by an oscillation amplitude of approximately 1 mm. The proposed bang-bang controller demonstrates high robustness to actuator failures, as the control decision is made independently for each actuator. The controller's performance under actuator failure scenarios is further evaluated in figures 2225, which present tracking results with 4, 7, 10, and 14 blocked valves out of 20, simulating actuator failures. Although the controller remains effective, Physical limitations due to failed actuators impact the system's performance. For example, with 7 and 10 out-of-service actuators, the robot can still track trajectories but is unable to access the upper part of the workspace due to unavailable actuators. These results highlight the importance of considering actuator failures in control design and the potential benefits of the proposed bang-bang controller in such scenarios. A novel closed-loop control scheme for binary actuated systems is presented, applicable to systems that are naturally stable without requiring an analytical model. The scheme comprises 2 controllers: a static iterative controller for point-to-point tasks and a dynamic controller for motion control tasks. The static controller utilizes a genetic algorithm to iteratively search for optimal actuator combinations, correcting system errors using experimentally identified influence vectors and the superposition principle. Experimental results demonstrate the controller's effectiveness and robustness against perturbations and actuator failures. The dynamic controller determines the on-off state of each actuator by comparing the direction of their influence vectors with the direction of a composite error vector. Despite bandwidth limitations, experimental results show high potential for motion tracking with robustness to perturbations and actuator failures. Future work should include real-time setup tests to evaluate the dynamic controller's full potential. The proposed controllers can serve as a base framework for future binary or cellular-like robots. Potential extensions include incorporating adaptive schemes for online identification and calibration of influence vectors, accommodating nonlinear behaviors and actuator failures, and expanding the influence vectors approach to non-binary robots by adding adjustable amplitudes. A hybrid controller that switches from the dynamic controller to the static controller to limit control activity when targets become static could also be developed. Implementing a positive non-zero threshold for the bang-bang controller may help moderate chattering behavior. A novel fault-tolerant control algorithm for binary robotic systems is presented, enabling operation even with up to 50% actuator failure. This research focuses on enhancing reliability and resilience in robotic manipulation tasks. The proposed algorithm utilizes an influence vector approach, allowing real-time adaptation to actuator faults within a dynamic model predictive control framework. This framework continuously updates control inputs based on the system's current state and estimated influence vectors of each actuator. Simulations and experiments on a 20-binary actuator robotic arm demonstrate the algorithm's efficacy, with successful task completion despite up to 14 actuator faults. The paper reviews various binary robotic systems, including those using dielectric elastomer, shape memory alloy, and pneumatic muscles. These technologies offer high power-to-weight ratios and low energy consumption but are limited by nonlinear behavior and hysteresis. Controlling large numbers of binary actuators poses challenges, including complex kinematic and dynamic models, the need for efficient control algorithms, and fault tolerance requirements. The authors suggest that developing new control paradigms and integrating sensors could address these challenges. The proposed fault-tolerant control algorithm represents a significant advancement in binary robotics, contributing to ongoing efforts to improve robotic system reliability and efficiency. This research paves the way for more robust and adaptable machines capable of performing complex tasks in various environments.